We're now going to give a bit more background on the absolute value of a number and also functions, just to make sure that you're comfortable with this concept. So let's first talk about the absolute value of a number. So the absolute value of a number A, all it represents is the distance from 0 on a number line. And in terms of notation, we denote it by absolute value of A. Distances are always positive. Okay, so we can say that the absolute value of a number is always greater or equal to 0. So say, for instance, we're looking at the absolute value of 2. The absolute value of 2 is just 2. And then for negative 2, it's also 2. And what this represents is that if you're at 2 here, you're just 2 units away from 0. And even if you're at number 2, you're still, in terms of distance, you're still only 2 units away. Okay, so this is how we think about the absolute value of a number. In the last video, when we were talking about the absolute value of a function, the absolute value of x, remember we said that if x was greater or equal to 0, we had x, and if x was less than 0, we had negative x. We had a plus part and a negative part. I'm going to go through with you how we obtained that picture that we drew. So we know that f of x is equal to x. It's just some straight line like this. Now, if we look at all the parts that are under y is equal to 0, so all the negative components, if we take the absolute value of this x, we need to flip those above this x-axis and make them positive. So negative 1 would become positive 1, negative 2 would become positive 2, so on and so forth. So what I'm going to do is I'm just going to flip my y values for the negative x-axis. And then if I also draw the positive side, that function in pink, that's what the absolute value of x looks like. Okay, so that's how we came up with that graph. Oh, I was supposed to draw it here. My bad. So that's how we came up with that graph. So whenever we have negative parts, we just flip them and make them positive. So in terms of writing the piecewise function, if we look at the part between negative infinity and 0, so the line that physically looks like this, okay, between negative infinity and 0, this is just a line with a negative slope. It's just negative x. Okay, so that's why we have our negative x for that one part. If we're looking between 0 and infinity, okay, and this is actually including 0, all right, we have a line now that looks like this, and that's just a positive line with slope 1, so we have f of x is equal to x. So now let's look at an example that's a tiny bit more complicated, but we're going to take the same approach. We're going to split this up into a positive case, so whatever we have in the absolute value, this 3x minus 2, and then we're also going to have the negative case of whatever's in the absolute value. So negative of 3x minus 2, so make sure to put the brackets there. And we do this if the stuff inside the absolute value sign is positive or equal to 0, and then if it's negative, that's when we take the negative case. And if we write it this way, then it's a lot easier to see how we get to the next step, how we get to describing this next function here, this absolute value function. We're going to have 3x minus 2. If we isolate for x, this 2 is going to come over here. We're going to divide by 3. So that happens if x is greater or equal to 2 over 3. But for the negative portion, I can write this as 2 minus 3x, and we're going to get that expression if our x is less than 2 over 3. Okay, so if you can jump straight to here, that's totally fine, but the in-between step on how to get from this expression, the absolute value, to writing it as a piecewise function, this is what we do. We look at the stuff inside the absolute value when it's positive, take the plus case, and then look at it when it's negative and take the minus case. And in terms of drawing it, if this was the function, if you wanted to draw the absolute value, okay, so basically a reflection about the x-axis, okay, I'm just going to flip this. All right, and then this is, oops, sorry. And then this, okay, I'll try to draw it beside, and that's the absolute value function. Okay, so this is my 3x minus 2, and we basically just reflected this part about the x-axis. All right. Now, properties of absolute values. So say we have a number that's greater than 0. Okay, whenever you see an expression absolute value of x is equal to a, so that either means that our x is equal to negative a, or our x is equal to a. So remember, we're either a distance, a away from 0, it doesn't matter on what side of the number line we are, either way we're distance a from our 0 value. When we have the absolute value of x is less than a, this corresponds to splitting this up into an inequality where x is going to be between positive a and negative a. Okay, so this looks like two open holes here. If we had less than or equal to, we would fill in these holes, we would color them in. But when you see that inequality expression, that's what it represents. If you see the inequality expression with absolute value of x being greater than a, that's the case where either x is going to be less than negative a, or x is going to be greater than a. Okay, so I'm not including the a or the negative a, so I'm going to have open holes here. But then I'm either talking about this section or this section. And that's just how we define these things. Okay, this is what they represent. So every time you see this, you can rewrite it like this. Every time you see this, you can rewrite it like that. So say we have this problem. Let's solve the absolute value of 2x plus 6 is greater or equal to 8. So what does this mean? So by definition, this means that the positive case will have the 2x plus 6 is greater or equal to 8, and then, or the negative case, where 2x plus 6 is going to be greater or equal to 8, but we can think about this as 2x plus 6 and then divide through by that negative, so it flips inequality and it puts the negative 8 there. You can either write it like this at first, or you can write it like this, whatever you prefer, personal preference. So let's look at this expression, our positive case first. So I'm going to bring this 6 over, so I have 2x is greater or equal to 2. Then I can divide by the 2, so I have x is greater or equal to 1. Okay, so greater or equal to 1, so including 1. So that part would represent this little line on our number line with the dot here. And if we look at this case, our negative case, okay, I'm going to bring the 6 over again. So I'm going to have 2x is less than or equal to negative 14. Divide through by the 2, so I get x is less than or equal to negative 7. So for this part on the number line, I have negative 7, including that negative 7, and then everything less than that. So this is what it looks like on the number line. And then these are our solutions here. What if we had absolute value of 2x minus 5 is less than 1? So this time we have an inequality with less than. So remember just what that means, that we take the thing in the absolute values, and then whatever that number is, I'm going to put positive on the right, negative on the left. And then we just isolate for x like we normally would. So I'm going to have to add 5 to everything in the inequality. Okay, to get rid of the 5 in the middle. So now my 2x is between 4 and 6. And now I can divide by 2 to get x's between 2 and 3. So on this number line, now not including 2 or 3, that's the values that I have on my number line. Now, let's look at one more. Okay, so what it looks like if we're dealing with other types of functions or other types of problems. So let's say that we have the function absolute value of x minus 3 divided by x minus 3. So let's talk about what our domain and range is. Okay, so first of all, this is an absolute value function, but it's also a rational function. So our bottom cannot be equal to 0. So we know for sure that the x minus 3 cannot be equal to 0. And what does this mean? This means that our x cannot be equal to 3. So our domain, we don't have any other issues here. Our domain is good up until 3. So I have negative infinity to 3, union 3 to infinity. Okay, it's just that one point that it's a problem. Now, let's look at the positive case of this. So let's look at the case where this 3 minus x is greater than 3, or when x is greater than 3, however you'd like to think about it. So my function can be written as f of x is equal to x minus 3 divided by x minus 3. These terms are the same, so the output of the function in our positive case, all this means is it's equal to 1. In the negative case, so when x is less than 3, or in other words, when x minus 3 is less than 0, that's when we would take the negative of the absolute value part. So minus x minus 3 divided by x minus 3. Again, these are the same terms, so they cancel, and this is the same as saying negative 1. So in other words, if we didn't like how this was written, it would be valid to also write the function as just being 1 if x is greater than 3, or negative 1 if x is less than 3. So on a plot here, if we drew this, we would have an open hole at 1, at 3, and then we would just have a line for all the values of x that are larger than this. And then if I'm to the left of 3, I'm also going to have a hole, and then I'm going to have a line to the left of all the x values from that, so all the negative numbers down towards the left. Okay, so this piecewise function is equivalent to this function. So what is our range in this case? Well, we can only have two values. We can have negative 1, or we can have positive 1. And because we can only have two values in terms of notation, this is when we use these squiggly brackets here. Okay, we can't do an interval because it's not values in between negative 1 to 1. It's discretely negative 1 or positive. So that's why we have our little squiggly brackets there. All right, so I hope you found that helpful. Hopefully not too intimidating, but I just wanted to give you a few examples of where the absolute value function could be used and how we analyze it. Thank you so much.